Last time we paused at examples of doing filtering. So we are doing filtering using the placement of zeros and poles on the Z plane. So make it close to the unit circle. Then the poles close to the frequency that we want to emphasize. We place 0 on the frequency that we want to remove. We want to nullify it from the input signal. So we're looking using the MATLAB example. So let me go back to that. And then I'm going to give some other practical examples of some practical devices, the digital resonator, the digital comb from the book. So we are using this example last time to look into how to place a pole in the zeros to do a filtering design. We have here playing the poles to generate a filter that amplify signal components. So here's the picture we saw last time. We start back here, and we are playing 8 zeros evenly around the unit circle. Therefore, the frequency component at omega equal to 0, omega equal to pi over 4, pi over 2, all those frequencies will be removed. It will basically, we generate in the frequency domain, the spectrum look like this. The spectrum look like this. We have those 8 nullified points on those 8 frequency positions along my unit circle. And it's very nice. All these frequency components of all these signals with those frequency components are removed to 0 because I placed the 0 exactly on the unit circle. When we look at the phase of this filter, this is a linear phase filter. And when you do a wrap up of 2 pi, and that will give you a straight line, of this phase. We really like a filter that has a linear phase because we know if it's a linear phase, that is just a pure delay. That's just a delay of any input you give me, I give you the delay. And this delay theoretically is the same for all frequency component in the original signal. I've not distinguished any of the frequency. Along the line, it gives me the same delay. Now we have a linear phase. The reason is that this filter is really an FIR filter, finite impulse response. So if you remember last time, what we get here is we are using this phase. Let me just write here. This HZ is equal to 1 subtract Z to the power -8. That's it. I only have the numerator. I do not have the denominator. So that is we call it as a B. The coefficient B is 1. Remember that 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, and then get a -1. And A is just a 1. So if you put this as a vector in MATLAB, A is a vector in MATLAB, it's 1. So I don't have a denominator. That gives me this one. And then we mentioned that H is Y over X. Therefore, YZ is XZ subtract XZ, Z to the power -8. So if you get into the time domain, Yn equal to Xn subtract Xn -8. So we just have a delayed term. You get one input, then I pick up the delayed input of 8 time units before, take the difference, subtract, take difference, and that will be my current output. So I have a finite impulse response where here, what is Hn? Hn is delta n and subtract delta n -8. So Hn in time domain, we have those 2 spikes at 0, another one at 8, but it's going this way. We have a finite support, meaning that within this time range, Hn has non-zero values, and that's a finite impulse response. I have finite. impulse response system. And that will guarantee a linear phase, something that we like. Okay. Now we look at the other one. So we have, this is the linear phase, and then I changed that a little bit. So B is 1. I swamped those coefficients. B is 1. A is this value. A is 1, 0, 0, 0. And we have a negative 0.9 because I don't want the pole to be under a unit circle. That will give me an unstable system. I want the pole to somewhere close to the unit circle, but inside. So I have a negative 0.9 here. The system here is HC. That is, numerator is 1. A is 1, B is 1. Denominator is 1, subtract 0.9 times z to the power negative 8. 1, 2, 3, 4, 5, 6, 8. All right. So this what we have is we got 8 poles. And the amplitude of the pole is 0.9. The phase is around 0 to 2 pi. So we can plot this out in a picture here. Here is the pole picture. And we got those 8 poles around the unit circle. What we want to do is we want to emphasize on these frequency components. Emphasize at the DC, at pi over 4, at pi over 2, and 3 pi over 4, pi, so on and so forth. Because my numerator is deformed to a constant, therefore I have zeros that is deformed onto the origin. I have 8 zeros on the origin. Theoretically, I have the same numbers of zeros in the poles. In this case, we said we don't have zeros because zeros is really determined by the polynomial of denominator. It's deformed as a constant, so it's all these zeros on the origin. But that doesn't affect my final effect of the frequency response. So we have here, frequency response is I got those 8 peaks on the frequency that I want to emphasize. 0, pi over 4, pi over 2, and so on and so forth, 8 of those. Now, on this picture, I want you to pay attention to the phase. The phase is nonlinear. You can see maybe a wrap around, it connected. We can do unwrap on MATLAB. You can see something. You got a trend. It's very nice, an up trend, but phase itself does not give you a straight line. It's nonlinear. An easy way to see that, of course, if you calculate the group delay will not give you a constant. And therefore, this is a nonlinear phase filter because it comes from an IIR system, impulse infinite response. Most likely an IIR will give you a nonlinear phase system. So let's look at another example of a digital resonator. Now the one we had from the MATLAB example, it can be we can call that a digital resonator, and we can call that a digital resonator is a resonate at certain frequency. That is, you emphasize on those frequency. We can also have a digital comb that you de-emphasize on those frequencies. So this is a textbook example from digital resonator. We want to design a digital resonator has only 2 frequencies. Actually, I will have 1 frequency I want to emphasize. So this emphasizes the frequency at omega 0. So I want to emphasize this frequency. Here is the frequency domain. This is 0. Digital resonator is a special bandpass filter. It's a very narrow bandpass filter. I just want the band around omega 0. If I want to have a real coefficiented filter, then I need to have a negative omega 0 term here as well. Translate onto the Z domain, we will see that I have a pole here, and then I have a complex conjugated pole around here. So that will give me real coefficients. From the previous discussion, we know how to do that. Well, we need to place the pole around frequency omega 0. place a pole around frequency negative omega 0, but the pole should be near the unit circle, but within the unit circle. Therefore, the amplitude here, R, is less than 1. R is less than 1. So we plate those conjugate poles here. The filter has a very large magnitude response in the vicinity of the pole location. So from this picture, you can see it's not ideal, but we have from negative omega 0, we have those two spikes. If the pole is very close to the inner circle, then these peaks will become sharper. Ideally, if I is equal to 1, and then these two peaks will point to infinity. So it looks like a straight line here going upwards. The filter is to resonate the frequency omega 0, therefore its name, called a digital resonator. Now, what about its phase? The angular position of the pole is nonlinear. From this picture we see, this is a highly nonlinear picture, and it's not a straight line. If the R is close to 1, this nonlinearity becomes dominant. You have those large turns. As we discussed before, so we can implement that using placing the poles. If you have a pole, which means you got something on the denominator, right? Its pole is coming from, it's really coming from AZ here, from denominator here. That'll give you the poles. If you have some concrete poles on the Z-plane, non-zero poles on the Z-plane, and then you will have this denominator, and therefore we have that, we got a feedback, right? This is Y, again, Y over X. So you got feedback. Therefore, this filter most likely is that is infinite impulse response filter. That gives me a nonlinearity. Again, to review, what is infinite response filter? So if you write this response, if it's causal, starting from 0, H0, H1, H2, I will have infinite many of those H's. It just goes on. It never becomes a 0, right? Because you have a feedback. If you really want to solve the difference equation, write it into these H's, so that will have infinite many of those H's. Digital resonator has many applications, including a narrow bandpass filtering, and includes a speech generator or speech synthesizer. Today's speech synthesizer is very close to a real human voice. So you need to, some way you need to generate the frequency components in the signal, make it sound like a human voice. And you can change the human voice, low pitch for male, high pitch for female, and change it to baby voice, and can do all kinds of things. And then you have to generate some specific frequency. That's why we use this resonator a lot. Let's look at how to find all these, find the mathematical expression for a digital resonator. So the resonate peak at or near omega equal to omega 0. And we know for a real coefficiented filter, I got two poles. So the two poles are on P1 and P2. That is given by that. It's the amplitude is R. R is less than 1. And the phase is what we want to design. We want to have the phase at omega. So we have e to the power j omega. And another pole is e to the power negative j omega. We can also select two zeros. For system, we two poles, two zeros. One choice is to locate the zeros at the origin, which means that you simply put this bz, which the denominator term, as a constant, b0. So I don't need to worry about the numerator term of my fractional expression. Numerator term is a constant. The other choice is to locate those two zeros, one at z equal to 1 and another at z equal to negative 1 on the Z plane. So you have two poles here and here. I can put two zeros at the origin. I can also put a 0 here equal to 1, 0 here at negative 1, which this point is frequency 0. This point is frequency pi. Therefore, at the two end, low frequency, high frequency, you want to make sure your signal component is completely nullified. And then it's really a bandpass filter. You have only the signal around here is emphasized. So let's look at the resonator with zeros at the origin. Let's look at a simple case. So I don't have the discussion for the numerator. I only have the denominator, have those two terms. Denominator, we have, this is P1, this is P2, okay? And in the frequency domain, so this part is z to the power -1 for the z domain. Now I'm looking everything in the frequency domain. So that is my h omega. It should look like that. It's very simple. I can just write it out. The thing is that I want to do two things. I want to first to determine this parameter B0. And then also I want to see, is my frequency filter h omega really give me the largest value at omega 0? It is really the largest. So we select B0 so that the amplitude of my filter on the frequency you want to resonate, that is 1. So let's normalize that. So you have a sharp peak, maybe like this. And I want to make sure here, this is 1. And ideally, these two, 0 and a pi, that will give me complete 0. Okay, if make this equal to 1, so we plug in here, and I know this h omega is 0. First, we replace omega with omega 0, and we putting this omega 0 here, omega 0 here. Sort out the numerator, it gives me this form. And then I put an absolute value sign here. So the absolute value sign, if you're putting here, that's my absolute value here. B is a constant. It's a real coefficient constant, so it still have a B0. R is a real number, so 1 subtract R is here. And then the absolute value of this term, that will give me square root 1 plus R squared, subtract 2R cosine 2 omega 0. And then make this equal to 1, I can find out this coefficient B0, and it's easy to derive. The B0 is given in this form. It's a real value. And then I want to check if my digital resonator really does its job to resonate at a frequency omega 0. I defined my filter h omega. So h omega is in this form. I defined two functions, u1 omega and u2 omega. So u1 omega and u2 omega is each one is this in this parenthesis. So what is that? Well, this in this parenthesis, you can also look at that as e to the power j omega subtract r times e to the power j omega 0. Okay, if I put it omega out and here put another omega out. So from my Z domain plane, this is my Z plane. I have this term is P1. Just exaggerate, it's much smaller than 1. So this is P1. This part is your frequency, omega. So that is the unit circle. So you are, as omega changes, I travel around the unit circle. Let's say I got a, here. So that is omega 0. I got a point here. From here to here, this is omega. So what is that? Well, these are the difference between these two complex numbers, right? So the difference between these two complex numbers, as you can solve for it, is you can think this is a vector, this is a vector. So it is this vector, and pointing to this first term, So this is the vector. It's really represent here. That is my, this is my U1Z, U1 omega, excuse me, U1 omega here. So if we understand from this picture, it looks like that. So so the U1 omega, if I'm looking at the absolute value. So actually, this is not U1 representing only the absolute value. The absolute value of that is square root 1 plus r squared subtract 2r cosine omega 0 subtract omega. That is the distance of this segment. And then the phase of that, the first phase is omega subtract theta 1 omega, where theta 1 is the phase of this term. So indeed, the phase is the difference between these two. And another one is omega subtract omega 2. I have another pole here, so it's same omega subtract that. These are the two differences. And you can also think because I have these two are on the denominator, therefore the phase of that, you should subtract these two phases. Now I'm only interested and focusing on absolute value of h. So I'm only focusing on these two parts, which is the real value, which is the absolute value of this part and the absolute value of this part. I want to check if this is really the best point, because U1 and U2 are on the denominator. Therefore, I want to minimize U1 and U2 in order to function as a resonator at a frequency that will give me a peak. To minimize U1 and U2 omega, with respect to omega, after some calculation, we find out the optimum value is at this. It's at a arc cosine 1 plus r squared over 2r times cosine omega 0. Now this omega is not exactly at omega 0. It's a little off. Right? The only time it gives me exactly at omega 0 is when r is equal to 1. If r equal to 1, meaning that I choose the pole on the unit circle, then this becomes 1, and arc cosine omega 0, that gives me omega 0. So that says that you are picking this pole here. You pick up this pole with omega 0, but for your resonator, the best point is not exactly here, but the best point is a little off here with the frequency. I'm exaggerating a little bit, but this angle is omega r. That's the best you can have. The reason is because I have some, I pose the pole near the unit circle. I also have the effect of zeros. Therefore, it will tune off a little bit to your original design. It's not exactly on omega 0. Similarly, we can discuss a digital resonator with the zeros z equal to 1 and z equal to -1. All we are doing here is we got those two numerators term here. And the absolute value of h omega, you have U1, U2, but you also have the numerator term here. You can check with the best position of omega give you the largest frequency. The actual resonant frequency is also altered. Again, that's due to the fact that r is less than 1. It's not on in a circle. Because I want to have the stability, some sacrifice is that I sacrifice the accuracy of the design filter. For this digital resonator, okay, in practice, the frequency is a little off. We know that's due to the pole. The other issues we haven't mathematically looked at it is the phase issue. It's a nonlinear phase. Nonlinear phase is something that we don't like. So we want to compensate then for phase nonlinearity. What we can do is using a so-called all-pass filter. All-pass filter, as we said, all-pass filter is passing the frequency across the entire spectrum. So the frequency of interest is from 0 to pi. The magnitude is equal to 1. Okay, within this window, this is the entire window, that the filter, the absolute value of the signal go through the filter. The only thing here that we can kind of manipulate is the phase term. The phase term, somehow we can design that. If the phase is exactly compensate of what you had before, And then maybe you can have a linear phase thing. So for example, I have a digital resonate here, which is nonlinear filter. And that's the input signal. Then I cascade a all-pass filter. Now, all-pass filter is not going to change anything with your resonate frequency, but somehow it can change the phase. By a well-designed all-pass filter, you can have a YN. A YN will, the entire signal will look like a linear phase. So YN is simply a delayed copy of XN, but with a very good amplitude on the amplitude emphasized on the frequency. How to construct an all-pass filter? A pure delay system is an all-pass filter. If my system is, the filter is Hz equal to Z to the power negative K. Now this is a finite impulse response. What it has is simply you have Xn, you go through the system, the output you take is Xn minus K, right? That's a pure delay. So that is a all-pass filter. Now how to look at that? Because H omega equal to e to the power negative j omega k. You take absolute value here. This is the unit circle. On the unit circle, therefore I give you 1. By definition, that is an all-pass filter. It's very simple. We can also design an all-pass filter in the second form. So this is coming from, let me write out one more line here, Hz. The denominator is A0, Z to the power negative 0, so Z to the power of 1, plus A1, Z to the power of 0, so it's 1, Z to the power negative 1, A2, Z to the power negative 2. Let me just write out those 4 terms, A3, Z to the power negative 3. What is the numerator? Numerator in this case, it's exactly, we change the order of the coefficients. So A3 plus A2, Z to the power negative 1, plus A1, Z to the power negative 2, plus A0, Z to the power negative 3. So we design a filter like that. The coefficient is numerator, denominator. They, for those two polynomials, they change the order, counting order. So we can put it in this general form. This is on the denominator, we have that. This is on the numerator. So you have exactly kind of doing this negative n, in my case, n equal to 3, negative n plus k. So you have that, okay? And then we can put this z to the power negative n to the front of this fraction. And in this fraction, I got those very nice form. The denominator is my polynomial, a as a function of z. And then the numerator becomes a as a function of z to the power negative 1. So everything is changed, z to the power negative k to z to the power positive k, right? So it looks like that. And az is this polynomial term. Okay. If this is the case, I am checking the amplitude of my h of my filter. So amplitude of h omega, which is also h omega times h negative omega, right? We know for on the z domain, it looks like that. That's my hz times hz conjugate. Hz conjugate, now z transform is a function of z to the power negative 1. Conjugate, it's a function of z to the power 1. So we have this inverse as my variable. So h1 over z. And because I'm looking at the frequency, so evaluate on the unit circle, z equal to e to the power j omega. If you plug in this, hz equal to that, and then we find out numerator, denominator, they cancel out. And we only, when z is also on the unit circle, then we have this equal to 1. So indeed, the amplitude square is equal to 1. The amplitude is equal to 1. This is a all-pass filter. For an all-pass filter, if Z is naught is a pole of Hz, then 1 over Z naught is a 0 of Hz. This comes directly from my previous discussion, where Hz has a form of AZ. Here's AC 0.81. Of course, I got something here. So if you have a pole, which this term equal to 1, equal to 0, then of course, you got the 1 over this pole, the inverse of that pole. It can satisfy the polynomial on the numerator, make this also equal to 0. Therefore, 1 over Z naught is a 0 of Hz. On the Z domain plot, we can see if I have a real pole here, then I will have a real 0 here. It's exactly the reciprocal 1 over A. Let's say the 0 here. If I have two of those poles here and here, complex conjugate, then the 0 is also easy to find. It's simply a reciprocal. So you 1 over that, you bring it to here. That is another 0. It's wrong here. And that is how an all-pass filter look like in the Z domain. So for an all-pass filter, if it's also causal and stable, if it's a stable system, we know that all these poles are within the unit circle. Therefore, all these zeros are outside the unit circle because they are a reciprocal of the poles if I have an all-pass filter. So the all-pass filter, if I have with all real coefficients, and so which means either you have zeros and the poles on the real axis, or you have complex conjugated pairs. So I can write it into this product form. The first one, these are the real zeros and the real poles, which indicated by alphas. These are the complex zeros and complex poles indicated by betas. There are n sub r real poles and the zeros, and sub c complex conjugate pair of poles and the zeros. If you are express the all-pass filter using this expression. For a causal and a stable system, we know all these poles should be within the unit circle. Therefore, for the real poles, all these alphas should be, it's real, but it's between -1 and 1. The beta are the poles, it's complex poles, and therefore the absolute value of beta should be less than 1 if my system is stable. Okay. What is all-pass filter for? We answer that. All-pass filter finds application as phase equalizer. It does not do anything with your amplitude, but it does change the phase. Right? When placed in cascade with a system that has an undesired phase response, a phase equalizer is designed to compensate for the poor phase characteristic of the system, and therefore to produce an overall linear phase response, or close to a linear phase response. And that is a good compensator. We're using all-pass filter to do that.